delta V. Okay, so that's what I substituted for delta U right here. Then I have plus V delta V, obviously they go up, plus V delta P. But what did I say I wanted to do here now? I'm going to work at constant pressure, so delta P must be 0. At constant pressure, delta P is 0. And then Q becomes the heat change at constant pressure. So if we work in a coffee cup calorimeter, the heat change, or the enthalpy, the heat change that we measure is really the enthalpy change. Okay. So if I want enthalpy change, I work in a coffee cup calorimeter. If I want the internal energy change, I work in a bomb calorimeter. Now the only difference between this number and this number is the pressure volume expansion.
Dr. Garrett, I'm
Yes.
sorry, can you repeat that? About the, if you're,
Oh,
I understand the internal for a bomb, but for the coffee cup,
yeah. Well, this was just rationalized. I could have just made that statement. If you work at constant pressure, the thermodynamic property you're measuring is called the enthalpy change. But I just went from this definition, well, here's my definition of the enthalpy change. It's U, the internal energy change, plus the pressure volume work. And I just wrote it as PV for the basic definition. Then I put in delta H because I can't really measure this number, I can't really measure this. I can certainly measure those two things, but that's a different problem. So anyhow, I just said I want to talk about the change in enthalpy. It must be the change in internal energy plus the change in the pressure volume product. Then I expanded that up using the rules of calculus, which, whether you believe me or not, this is what it gives you. Then I went up here, and here was my definition for the internal energy change for the system. And this is the enthalpy change for the system that I must be talking about. And so I substituted this thing for delta U. Then I just did the algebra. And so I have Q minus P delta V plus this P delta V. These must be the same number. So they subtract out. In other words, if I have minus P delta V plus P delta V, and it's the same pressure and the same delta V, it's the same number, so I'm just adding and subtracting the same number. Then the only term that's left is Q plus V delta P, but I said we're going to work at constant pressure. That's what the bomb calorimeter does, because the thing's free to expand and contract inside this loosely fitting lid. So the system expands and contracts as it wishes. So the pressure stays constant, and we haven't specified what that pressure is, but it doesn't change throughout the course of the experiment. So since delta P is equal to 0, that's the only term that's left here. When we talk about enthalpy changes, we're really measuring the heat change at constant pressure. The bomb calorimeter measures the heat change at constant volume.
and that's what the subscript P represents?
Yeah, it means that Q sub P, you're measuring pressure, you're measuring the heat change at constant pressure, just like Q sub V here means you're measuring the heat change at constant volume, and then that's what constant volume means, that's what constant pressure means. Okay. And the next thing I'm going to say, because there's only one problem I'm going to do out of this, and some years I don't do it, but other years I do. And last year I told the students I probably will do this next year, so maybe I have to do that. What's the difference between delta H and delta P besides the fact that delta H and delta U, besides the fact that you're measuring constant pressure and constant volume? Well, if I have reactions which only have solids and liquids in, For instance, if I have, what's a good one? I dissolve NaOH, I dissolve HCl, makes a solution of sodium chloride. In other words, all that's left are the ions plus water. All of those are liquids or dissolved in solutions. When I look at delta U for this reaction, or I look at delta H, I get the same number. Now, it's not exactly the same, but typical numbers for delta H or delta U, hundreds or thousands of kilojoules. Either one of these would be about that sort of number. Now, if I measure the densities of these different components in the original solutions and the final solutions, and I can calculate the change in volume. And if I examine that delta PV term, it affects that place. But your data usually only has numbers in this place and this place, and the fact that when you're working in liquids and solid, theoretically it affects this place, it doesn't affect your actual numbers. Okay? So when the reactions involve only solids or liquids, because the densities are very similar for solids and liquids, and the total volume change between the reactant side and the product side of the reaction is essentially zero. There's some volume change, unless everything had exactly the same densities, I guess. But that would be a really unusual case. And in general, for solids and liquids, the delta PV is almost zero. It's so small, it doesn't affect our normal numbers that we have for the heat changes in reactions. Okay? So that's obviously not the question I'm going to ask you. The question is going to be calculating the difference between delta H and delta U when we're working with gases. Then, let me do it like this. PV equals nRT. Okay, so far so good. Then if I went delta PV, and the reason I did this, we always talk about something happening at a constant temperature. And you say, how can that happen if I'm doing calorimetry, and I erased the thing I needed over here, but it's easy enough to write. You always measure Q by doing a reaction where you have delta T. But yet you see your data given for the heat change at 298, or the heat change at 241, or the heat change at some temperature. How can you get a delta H at a particular temperature if you have to get it from a calorimetry experiment where you have to put in material, have the temperature of the calorimeter change, you measure delta T. And the way you do it is, for problems, what I usually do is like, so if the temperature of the calorimeter goes from 24 to 26, the average temperature is 25 degrees. So that's one of the ways of getting around it for simple problems. The way you really do it in the lab, I'll just put delta H if I'm measuring that, delta T. And first you put a lot of material in the calorimeter. The more material you put in, the bigger the heat change. So you get a big delta H here. You put an In other words, you get a big temperature change and a big number for delta H. Then you put less material, and less material, and less material. Each time you put less material in the calorimeter and have the reaction occur, you get a smaller delta T. And finally, you can't see anything happening because you have so little material, but what you do is you go back to here, and there's the enthalpy change at a fixed temperature. Okay? So you do it by extrapolation, and we don't have to worry about that because this isn't a course in physical chemistry and advanced thermodynamics or anything where you have to worry about that. But people always say, how come you can say, here's delta H at 298.15? And you say, that's the experiment. You're not going to do it, but there is a way of getting to it. And the easy way is just to average the temperatures. Okay. It's not as good as this. This is the way it's actually. And when you look at thermodynamic data, it changes slightly from year to year. Not because the reaction is changing, but because people have better techniques for measuring all these different things. So you look at an old book and you see one number for delta H for a particular reaction. A newer book will give you a slightly different number and maybe an extra bit of precision because they have better measuring techniques. These are all things that are the practical sides of calorimetry. Nothing we have to worry about, but when we do this, RT. Let's pick a good reaction. What's a good reaction? N2 gas plus 3H2 gas equals 2NH3 gas. What's delta N for that reaction? We did this before. Where did we do this before? A relationship between K sub P and K sub C. Remember that? RT to the delta N. You don't remember that? That was only 2 weeks ago. 4 weeks ago. Semester's almost over. You forgot it already. What are you going to do when you get to the final? It's time to start reviewing for the final already. Forgot it. Anyhow, we saw delta N before. It's moles of gaseous products minus moles of gaseous reactants. For this one, -2. And let's say I'm working at 300 K, which is near room temperature, a little higher. I'm not going to put the minus sign. There's delta N, RT, 16 times 300. Right, 16 times 300. It's about 4.8 kilojoules. That means, coming back to this sample number, if you're working with gas phase reactions or a reaction that has at least one gas in it, it's going to affect this place. The difference between delta H and delta U. So when you have gases involved in the chemical reaction, delta H is not equal to delta U approximately, and you can calculate the difference from this formula. So there's the thing you need to know if you're going back and forth between delta H and delta U, and I'll probably ask you to do that sometime.